This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So, welcome to Control Systems class. My name is Dragan Nesic, and I'll teach you this subject this semester. I was looking around to see if there are some familiar faces. Fortunately, there are not many. This subject is taught in 2 semesters, and there are some just differences in terms of delivery, but the material is the same. So if you did this subject in the first semester, I mean, I'm covering the same material. All right, so let's first do some preliminaries. You already know your timetable, and I mean, all lectures will be in this theater, Rivet Theater, except for potentially some, tutorial type lectures which will be in the Wright Theater. Now, these will be organized as we go, maybe as needed, and I will usually announce them before we have one of these. I think we will start from next week. I'll have to just look at the schedule, but probably we will start from next week, and probably we will run these lectures most of semester, right? They are optional, so this is where I will be doing examples, right? So in lecture times I will just present the material, but these optional lectures are just there to help you, because I'm a nice guy. I like to help students. So, because, I don't like to see familiar faces over and over again. So we will do this probably from next week. And then obviously, lecture slides are on LMS. Note that I would be following the material in resources lecture slides. So that's what I generated. There are quizzes accompanying each lecture. Sometimes the material may cover other lectures as well. These quizzes are just there to help you self-assess. This is the instantaneous feedback you get on your learning. Often students say we didn't get enough feedback. Well, I spent 1 semester generating these questions to help you get feedback straight away on how you understand the lecture material. There are also lecture notes which basically cover the same material. They may have a bit more detail at times, and they're provided for completeness. But as I said, I'm following the lecture slides that I generated. We are loosely following this textbook. So if you are going to enroll in advanced control, then this book is a good buy, because we try to teach both control systems and advanced control systems from the same textbook. It covers most of the stuff, not everything. Right? So this is a good buy. I will teach you about disturbances and perturbations. So this was a disturbance in my lecture, and I handled it well. I'm robust. All right, so there are other texts. So Franklin's book and Ogata's book are classics. And why I emphasize these books is because they have a lot of solved examples. Students often ask me, can you give us heaps of solved examples? These books have them, and you would have a lot of copies in the library. So Ogata would have a lot of solved questions after each chapter, and then a lot of unsolved questions. So it's a good balance between really just learning how to solve questions by following solved examples, and then attempting those unsolved questions by yourself. So very good books. I highly recommend both of them. They nicely complement and you know, elaborate further on this material. PID control I pretty much took from this book. So we will cover so-called PID control. So Ostrom and Murray's book is a great book. And again, you know, this one is actually good because it's free. You go just to this website and you get it for free. It's a good thing. And then if you're really into maths and if you want to study for perhaps towards future research, PhD, things like that, then this book is a very good read. It has much more sort of mathematically rigorous material with proofs and more advanced stuff. So that's also for interested readers. Not really necessary, but for interested readers, this is a good read. So this is like a Persian carpet, stuff that we will cover this semester. I won't go into details of each of these topics. You would learn a lot, I hope. And we will look at, I don't know, introduction to control systems, just so you learn the concepts. Then we will look at analysis, different types of analysis. So differential equations, Laplace transforms, frequency domain analysis like body diagrams, Nyquist criterion. And we will also do a lot of design. So we will look at PID control, so that stands for proportional integral derivative control. We will look at pole placement, internal model principle, a lot of powerful tools. Loop shaping in frequency domain using body diagrams would be like a proud achievement in this subject, and it's all about design. So you will learn how to design control systems. All right. Workshops. Workshops are in EDS 8. You can assign yourself, you probably already did, to one of the groups. You would work in groups of 3. There will be some reports for some of the workshops. So first couple of workshops, there are no reports, but then the last 2 do have reports. You would work in groups, and more instructions will be given by the tutors. All workshops will start in week 3, except for workshops that are on Friday. Why is that? Does anyone know? Yeah, grand final. So footy grand final is on one of the Fridays in September, last week, I think, in September. And these people will start in week 2, so next week. So Friday workshop starts next week. And all others week after that. Head tutor is Jing Mo. Please contact her, all things to do with workshops. If you need to change times, if you know there are any issues, you're sick, please contact Jing. She would be dealing with these sort of questions. If you contact me, I will just forward your email to her. You can save me just one. So press a button by just contacting her directly. And she would contact me for any issues that require perhaps more sort of executive decisions, right? But she's a first point of contact. All right, so what is the assessment? There will be a couple of reports or workshops. You would be playing with Lego robots. It's a cool lab, I think. And 2 reports will be marked. There will be mid-semester test. I usually organize this test online. It will be during one of the lecture times so that we prevent copying. Because in the past, people would tell me, oh, I have I work in a pizza shop at 10 a.m. right? So you believe them, right? So they tell you they work in a pizza shop, and then you give them like 4 hours or 5 hours, and you can see how the performance of students improves by the 5th hour. It starts pretty poorly, right? And then it improves by the 5th hour. So if we organize it during the lecture time, this doesn't happen. You are all on your own. They test you for your knowledge. It's an important feedback to you. I know people are sort of interested to just get a good mark, but if the midterm test is an opportunity for you to get an honest feedback on how you are doing. If you have problems, you need to talk to me. I'm here to help you, right? So it goes without saying, please come and talk to me. I will repeat that many times during the semester, but I want to emphasize that I'm here to help, and please contact me if you are struggling with the material. There will be final written exam, which is worth 70%. It's a hurdle. You have to pass the exam to pass the subject. So you can get 100% of workshops and midterm, yet fail the overall subject. So exam is an important, big deal, right? So pay attention to that. It's 3 hours, typical thing, 15 minutes reading time. You know, we'll talk about this more when the time is right. Office hours for myself are on Tuesdays, 3 to 4. I try to look at non-overlaps with workshops. You know, I know you might have still clashes with some other subjects. I couldn't check that. Everyone is doing different subjects. But at least this shouldn't overlap with any workshops that we are doing, or lectures, obviously. I'm sitting on 5th floor at the electrical engineering building. I think it's 193 building. And yeah, if you have any questions, please send me an email. I do encourage you to see me throughout the semester, because, you know, just before the exam, it's like Disneyland in front of my office, right? So there are big lines. It's like Space Mountain. Big lines, everyone wants to talk to me, piece of me, you know, but I'm, you know, really lonely during the semester visitation hours, because, you know, I like to make new friends. All right, so I will encourage you to use these consultation hours as much as you can. And that's all I have to say in terms of just general information. Are there any questions? All right, it's early morning, early in the semester. I hope I entice you to interact more. I do encourage you to stop me and ask questions. I love questions. So I know that some people are shy, but we'll work on that, all right? So let's see how we go. So introduction to control systems. I know that some of you may have even done subjects related to control. Has anyone ever, can I see show of hands if you've done a control subject in the past? A few hands, but majority has not. All right. So I apologize to people who know everything about control, because yeah, we need to go through this for the benefit of everyone else. So here's the introduction to this subject. Well, you may not realize, but control systems are everywhere, literally everywhere. Pick any device, I mean TV, your iPad, iPhone, any device will have heaps of control loops. Here I listed just a couple that are obvious. I mean, aircraft, you know, they often have things called autopilots. I mean, it entered, you know, popular language. I'm an autopilot, right? So that means that there is a control system busily working there and maintaining the altitude, the speed, etc. of the aircraft. A similar thing exists in any car, cruise control, most cars, cruise control. You set your desired speed and off it goes, right? Doesn't matter whether you go uphill or downhill, it should maintain the speed. I mean, robots, it's quite obvious that these, you know, machines need to have very sophisticated controls. Without controls, any of these is just a piece of junk. It's just a piece of just metal that's useless. If you don't have an algorithm, a control algorithm that controls your robot, it's useless. You may just sell it for scrap metal. So wind farms, what's this? Well, this is a cell. I mean, my daughter is doing a PhD in WEHI here in Melbourne Uni, and she's doing, you know, cancer research, genes, all that. There are heaps of regulatory networks inside our body. There are triggers, hormones, that basically trigger certain processes. Dying of a cell may be triggered by an internal loop, right? Breathing, blood sugar level in our body, they are all regulated, right? So our circadian rhythm, when we wake, when we sleep, right, is regulated by a control mechanism called circadian rhythm. Jet lag is basically your control mechanism is sort of not attuned to the day-night cycle in the new country. I just came from Europe. It takes me about a week for my control mechanism to adjust, to recover from jet lag, etc., etc. I hope that you would, after this lecture, already start appreciating the importance of control systems. So here is the outline of the lecture. I would first provide a bit of introduction, motivation, tell you maybe about some success stories. We like to brag in control, right? So we want to take credit for things. Why? Because it's actually often overlooked. Often control engineering is overlooked. It's everywhere, but many of you would not know that it exists. It just busily works in the background, making things work, right? So I will present an example with some terminology. One purpose of this subject is to teach you the language of control engineering. Obviously, we want to also equip you with tools, but also the language is important. So I will introduce some of the language in this lecture. And then block diagram is an important sort of part of our dictionary in control engineering, and I will introduce block diagram, and then just wrap up with conclusions. All right, so my claim is perhaps that we are a dominant species because we learned to control our environment. And this has been going on much longer than you may think. So, for instance, I was reading a book about history of humankind, Sapiens. I don't know whether you've heard about the book. But, in that book, it's a bit sort of maybe not flattering sort of summary of the effects of humans on nature, starting from Stone Age. As people spread, if you believe in that theory that they spread somewhere from Africa, as they were going to new lands, wherever they came, big mammals disappear within 1,000 years. Apparently, in Australia, all megafauna died within a couple of thousand years after human arrival. Eucalyptus trees, forests, apparently were not the dominant species until humans arrived, because apparently they were burning the bush. It was better for them. They get food, they can move around. So they were actually controlling their environment already with the advent of fire. So fire, multiple uses. You can start eating foods that otherwise you couldn't. Cooking, right? Warmth. You control sort of, predators. You defend yourself from predators. Clothes, you can't imagine people conquering, the North Pole and Canada without clothes, right? Etc. So building cities, we live in a very sort of regulated, controlled society. And it shouldn't come as a surprise to you that control engineering plays a crucial role in any technological advances. In agriculture, in, just infrastructure, any sort of infrastructure, buildings, household appliances, transport, defense, any device you can think of would have some sort of control in it. So in order to really talk about control systems, it's a useful thing to reflect on what we mean by a system. You can think of a system as a bunch of things, right, that work together. Actually, anything is a system. We talk about the solar system. Share market is a system, economic system. We talk about social networks. Control scientists these days analyze interactions on social networks, and they try to maybe look at advertising. What works, what doesn't. But they develop and analyze mathematical models of how humans behave in a network situation. So there are things called consensus. When do people reach consensus, right? In terms of their opinions, etc., etc. So it's a rather, so notion of a system is a very broad notion. Pretty much anything, a single cell can be a system, a solar system, galaxy, you know, anything really is a system. Now, control systems are a special class of systems in which we want to control a certain physical variable. What physical variable we're talking about, that depends on the application. It can be motion in a robot or a car. It can be temperature in a room. It can be anything, really. When you are taking a photo, there is a zoom. There's a control mechanism there, right? To adjust, like the zoom, so that you get a clear photo, etc. So we will talk in this subject predominantly about control systems. Now, why do we want to even study this subject? I hope that I already indicated that these things are prevalent and very useful. Now let's, look more closely at, the motivation. So the first statement is that these systems are prevalent, right? And they are actually essential. The red words in this slide are the keywords. They are prevalent, control systems are prevalent and essential in a range of different systems, both for engineered systems and for natural systems. Right? So when you get diabetes, that's basically your control system for regulation of blood glucose in your blood, and it's not working. And that's dangerous to your health. Cancer is basically uncontrolled growth of cells. The cells just go crazy and start growing, and we still don't know how to find a stop button, right? That's where all the cancer research is sort of concentrating. So anyway, these control systems are prevalent and essential. Let's look at prevalence. So I listed here just a small subset of applications of control systems. This is a small subset. And you can see here that it pretty much touches upon any area of your life. You might be eating food that was produced in controlled environments. I had for a few years a person who works in mushroom industry, not funny mushrooms, just mushrooms. And this turns out to be a very complicated control system because you want to maintain the right environment for mushrooms to grow. You want to have as good harvest as possible, and that requires careful control of humidity, temperature, etc. Right? So, look, this is just a subset of possible applications of control. These days, control has found its place in every area of science as well. In medical science, control engineers are looking at basically designing artificial pancreas. So there are sensors attached to your body that measure the blood glucose levels, and there is a device that can pump glucose into your blood, insulin, right? Some of them will have also glucose because when the blood sugar falls down, that's a dangerous thing. So some pumps actually have both insulin and glucose. And actually, there is evidence that these devices are working very well. There is more and more evidence if you read research literature that these devices are successful in clinical trials, right? So, look, you can find control engineering pretty much everywhere. Unfortunately, many people are unaware of its importance. So I hope at least that you would appreciate it more after doing this subject. Now, that was about prevalence. It's everywhere. Prevalence means it's everywhere. How about its importance? Well, I said that it plays an essential role. Actually, I would say this is an enabling technology. So someone designs a robot, And then a control engineer designs a control algorithm and makes that robot useful for something. Maybe in automotive industry, they are welding, they are painting cars, they're doing all sorts of useful things. But without a control algorithm, robot is absolutely useless, right? There are lots of examples where you can achieve high performance and precision by using control. Precision surgery is one example. Right? There are lots of repetitive tasks that can be done in a controlled fashion. Assembly lines in automotive industry have been around for a century, and there was a lot of automatic control that enabled mass production of cars. Control was essential in this case. Reduce waste and emissions. There is more and more stringent regulations in terms of emissions in transport. So governments impose on car manufacturers certain rules. You can't pollute as much as you want. So then that poses a sort of challenge for control engineers to design control algorithms that will achieve this, reduced sort of pollutants. Also improved fuel and energy efficiency, especially when you do advanced control. That's the subject that follows up from this one. You would learn about optimal control, and that's where you find control algorithms that are best in a certain sense. For instance, they use least energy and still achieve the task. In some cases, you achieve better safety and operation. In military, they love drones. They love these robots that have visuals. Why? Because they don't send people. You don't kill people to dismantle a mine or whatever, or find whether there's a leakage of something dangerous. You just send a drone and remotely operate. They love it. And then operation of complex systems. I mean, you may have heard of the notions such as smart grid. That's power grid, which is very carefully controlled. Smart transport is basically transport where cars can talk to each other. For what reason? Well, maybe for safety, you don't want to have car crashes. For efficiency, you want to reduce traffic jams. Control is very important for improving the happiness index, right? You just reduce frustration while driving because, you reduce traffic congestions, perhaps. So that's all about smart highways, etc., etc., etc. Okay? By the way, internet is one of the most complex man-made systems, very complex, and it works. It works. You do get access to internet. It's not that your next door neighbor only has exclusive access. There is an algorithm behind internet that provides fair access to the resource. Okay? So that's again controlled. Brain is one of the most complicated natural systems, and there is a lot of control mechanisms within the brain that make us think, do, be creative, do all sorts of things. All right, so I want to just go now to a very specific success story. So, do you know anything about Industrial Revolution? Have you learned about Industrial Revolution in school? Sometimes called the first Industrial Revolution. Does anyone know what it was? Why do we call it Industrial Revolution?
Because it changed the way our industries work. We had a lot of small, medium enterprises, but after Industrial Revolution, we could mass produce things.
Yes, we could. Mass production, that's a good one. Do you know which area of industry was most affected?
Oil.
Sorry?
Oil.
Oil. I wouldn't go to oil. That was the maybe coal time. People were still burning coal at that time. Yeah. It's textiles. You could really produce massively cloth. My grandmother had a loom, she made cloth from thread. You first shear a sheep, then you create thread from the wool, and then you can start making cloth. Now, you could massively produce, with these automated looms, you could massively produce thread, and also, cloth later on. So, it turns out that, so this is basically, look, there are these looms that basically make thread out of wood, right? And you could have heaps of them running at the same, spinning at the same time, and control system was at the heart of this device. And this actually fueled industrial revolution. Transport was another one. I mean, all the railroads started booming, a bit later after the industrial revolution. But let's talk about the control system, because I'm, interested to uncover for you this sort of little control system that made all this happen. All right, so how many of you have heard of Watt? Yeah. What was he famous for? Sorry? Well, you say steam engine, but actually the control mechanism behind steam engine was the actually intellectual property that I think it made it work. So if you see, so how does steam engine work? You have a boiler full of water. You have a guy, I don't know whether you liked Western movies, guys shouting, Indians are running behind the train, guys shouting more. So that creates heat. Heat converts water to steam under pressure. And then this pressure can be used to power a turbine. That's the idea, right? So basically, steam under pressure, so basically are converting thermal energy of coal into a mechanical energy. A very cool thing for people when we realize that we can convert one type of energy into another. Right? Now, this device here is called Watt's governor, or flyball governor. So this red circle on that big picture is basically enhanced here. So what you have there is a mechanical sensor which is connected to a valve that either opens or closes, the pipe that feeds steam to the turbine, to pistons, right? So basically, by opening and closing the valve, you can control maybe the speed at which the turbine rotates. Why is this important? Well, the quality of the thread that you make using that machine will be better. If it starts spinning faster, then you get thinner thread. If it starts spinning slower, you get a thicker thread. We're going to have a uniformly thick thread, and then maintaining the velocity of rotation of the turbine, right? Steam turbine is important. So how does this work? So this thing here is connected through some gears to the turbine shaft. So there is maybe turbine, right? So there are some blades. You would hit those blades with steam under pressure, and then that moves the shaft. Now the rotational speed of the shaft, we want to maintain it, because that's what would determine the quality of the product, the equal thickness of the thread. So how does this device work? Well, this is where I will start using my body as a teaching tool. So imagine that my hands are those two little sort of hands of this device. So these two balls have certain mass, and this device would measure the speed of the shaft. Through gears, it's attached to the shaft, so it would rotate at a speed proportional to the speed of the shaft. As it rotates, if it rotates faster, look what happens to my hands, they spread. But if you connect then this sort of movement of these arms to the valve, you can regulate it. But you can regulate how much you open or close the valve. And if designed properly, and this is crucial, if designed properly, this device could maintain the rotational speed of the shaft constant, or very close to constant, which would basically guarantee quality of the product. Okay? What turned out to be very interesting is Maxwell. You heard of Maxwell? Electrical engineers in the room? Maxwell's equations? Yeah? So, big guy. So Maxwell, you may not know, but he got interested in design of these systems. Why? People realize that depending on your design, how big these balls are, how long these levers are, you know, how you design the whole system, you might either have very nice behavior, like stable behavior, where you really maintain the speed you want, or they go nuts, right? So they would sort of oscillate between very fast to slow, break things. So people didn't understand what the heck is going on, right? So if you have no idea, there was no theory, mathematical theory, or engineering tools to design these systems. So Maxwell, among other things, was the first person who looked at theoretical aspects of controller design. He wanted to understand why these devices work sometimes and sometimes they don't. So what he did was, he was the first one to rigorously analyze dynamical or so-called stability properties of these systems. Now, Maxwell posed a problem, but it was a difficult problem to resolve. We will talk about this more when I start talking about Raoult-Hertz criterion. But it turns out that this problem was regarded by mathematical society as such an important problem that there was a competition. They said, okay, if someone solves this problem, you get an award. So it turns out that Ralph won this Adams Prize for his work. He basically solved the problem of stability. So the question was, if I have a mathematical model of a system, what conditions would guarantee that the system would be stable? Raoult solved this problem, right? But Maxwell posed it. This is one example, and this is often the case, where technology went ahead of mathematics and motivated mathematics. And then mathematicians first look at this simply as a mathematical interesting question, and now we teach it to our students. That's a cool thing of translation from science to real-world engineering. Okay? There are a couple of other very successful stories of control. If you go to these links, it's a very cool thing, especially the first one, the story of first powered successful flight by Wright brothers, 1901. So they had a bicycle shop, and then they decided to, move into another business. They wanted to produce planes, so from bicycles to planes. They managed to fly a plane for the first time in history of humankind. People did fly in balloons. That was all flying, but this was powered flight. Now, just prior to this discovery or this success, people already knew the theory, right, of flight, what they needed to do. But what was missing is control. The aircraft is inherently an unstable system. You turn off all the controls on the airplane and it just falls down. Right? You have to actively control it. It's an inherently unstable system. So without control, there wouldn't be, we wouldn't have, opportunity to travel so much, right? And many more. There are many more success stories. So I encourage you to read some of these. All right. Now I want to move more into some abstractions and terminology. So we would describe, it turns out that describing systems in a very abstract form, using these so-called block diagrams, is a very powerful tool. Very powerful tool. So I would say, well, suppose you have scales, you want to weigh yourself, that's a system. I would say I would denote any system by a block. It can be a subsystem of a system. That's like a box. That's the sort of notation I use to represent systems. And I would say input to the system is any sort of physical variable that affects the system behavior. So in this case, your weight, when you step on the scales, your weight is the input to the system. Right? Whatever is on top of the scales, right, is the input to the system. And what could be the output of the system? Well, the deflection of the gauge. You are interested in this variable, you want to know what you weigh, and that will be the outcome of the behavioral system that you are interested in. So it turns out that, you know, thinking about systems in this abstract way, where inside boxes I represent like them by system models, and all these arrows represent some physical signals. In this case, input is the person's weight, and output is the, you know, displacement of the gauge, deflection of the gauge. Well, it turns out that many systems, pretty much any system, can be represented in this way. And that would turn out to be very useful for engineering design. It turns out now, like, it looks like, oh, this is, you know, Mickey Mouse stuff. Of course, I can draw a box, right? But, you know, you will see that it's a very powerful representation of systems, and we will use them as tools. So you may ask yourself, well, what is this system model? Well, system model is a mathematical description of the dynamics of behavior of the system, the dynamics of your system. So pretty much any dynamical behavior of a system is captured by your system model to some extent. We will talk about models in more detail, but at this stage I can just say we will look at differential equations, we will look at so-called transfer functions, or frequency response, body diagrams. So you will learn to model systems in different ways, and then you will use these different models for analysis and design of control systems. Each of these tools is an important sort of feather in your hat. As a control engineer, you need to learn a lot of tools, right? And then we will make them work. We will show you how to use these tools to solve all sorts of problems. We will always use model-based design and analysis, and models could be a differential equation, or a transfer function, or frequency response, or something else, right? In this subject, we will concentrate on these: differential equations, transfer functions, frequency response. All right, so we have a bit more time, so I just want to present one example where, you know, you're more familiar with. It's winter, you know, often you need to turn on heating when you come home, and, you know, we want to analyze a little bit in more detail what's inside this heat, you know, closed loop system inside, like the room temperature control. So what's presented here, we have a room. Here we have a door that's open, so we have heat sink. You know, if you go to Europe and you keep a window open, you know, many people would just go and close it straight away. It's freezing outside in winter, right? Here we can still cope. But anyway, what do we have? Which parts do we have in the room temperature control? Well, here we have a sensor that measures true temperature in the room. What is this? What does this thing do? Yeah, desired temperature. We set here desired temperature. You come home, you say, oh, I want 25 or whatever, 18 degrees in my room. You set desired temperature. You have to tell your system what you want from it, right? But then you also need to measure, right, something. In this case, we can measure the true temperature. So desired and true temperature are taken to control algorithm that compares them, does some magic, and turns on or off the heaters. Or it may be even coolers. Maybe this is an air conditioning system. So it has maybe heating and cooling. I would call this, you know, an actuator in this system. So this basically actuator can affect the behavior of the system. Right? Sensors measure what is happening in the system. Actuators affect the system directly. Right? So, and then, you know, we have all sorts of, you know, disturbances, outside temperature being, you know, very important disturbance. As the temperature outside changes, then if it's a sunny day, we get heat coming into the room through windows, through radiation, but also through conduction, through walls. If you have good insulation, then you are better insulated from oscillations of temperature outside, but it will still affect you, right? So obviously, depending on the properties of the room, of the actuator, of the sensor, and your control algorithm, you might have that this system really maintains nicely temperature you want, maybe 20 degrees or whatever, but you can also have this system, you turn it on, and it just keeps heating until it's like 2,000 degrees in it. Or it can oscillate until, to minus 20, to plus 20, or to 200. You can design, dynamics here is something that you need to carefully design. And that's what you guys would learn to do. You would learn to design this control algorithm, take the model of the actuator, room, sensor, etc., and then you would design the brain. Control algorithm is the brain of the system. So you will design that, learn how to design that. Just a few terms. I would call a room a plant. Anything you want to control is a plant. A car, if you want to control a car, is a plant. In this case, room is a plant. Right? Sensor, thermometer, is a measurement device. So basically, whatever measures something, we will call them sensors. Actuator, in this case, is a heater. That's a device that can actually affect the dynamics, the behavior of your plant. Right? In a car, what would be an actuator? The engine, yeah. Steering wheel, right? Brakes, they're all actuators. You can affect them, right? So there are all these actuators in a car. Now, output variable is a variable that we want to control. In this case, the true temperature in the room is the output. The disturbance, in this case, is a variable you can't control, but it still affects your system. So for instance, in a car, sort of example, cruise control example, the slope of the road is a disturbance. If you drive on a flat road, it's different from when you're driving up a mountain. So you need to press the accelerator a bit harder to maintain the speed, right? And also, what we will often use is noise. The term noise. That is basically some sort of small, maybe amplitude, high frequency signal that just sort of doesn't allow you to get the true reading maybe of your sensors. But if it's a digital sensor, you might find that the measurement really oscillates. It never gets the true temperature, but it's affected by this noise, so-called noise. We will talk about this more later on in the subject. So it turns out that you can represent, using these boxes and arrows, you can represent the room temperature control using a block diagram now that looks like this. So you have a controller. This controller takes desired output. What was the desired output in the room temperature example? Desired temperature, right? Then this is the plant, that's your room. This is your heater, right? This is your sensor, in this case thermometer. So thermometer basically takes the measurement of the temperature from the plant, passes it to controller. Controller also takes the information about desired temperature, and then if you design this thing carefully, it would work like magic. And you will learn how to design them carefully. What's really important in this figure is the so-called feedback loop. Note that the arrows here that represent signals, right, are going in this direction, and then this arrow takes, some measurement of temperature, passes to sensor, sensor passes it back. There is this circular sort of arrow, sort of loop inside this picture. That's called the feedback loop. Control systems that we will learn about in this subject rely heavily on these feedback mechanisms. And we will explain in the next lecture the importance of these feedback mechanisms. All right, so I think I'm very happy with myself. It's just 1 minute before the end of the lecture. I paced myself very well. So just what you should take out of this lecture. First, control systems are important, they are prevalent, they are everywhere. They are an enabling technology. Without them, you won't have, many systems working. Can you just keep quiet, please? Thank you. Block diagrams are very important for abstractly modeling our system. It's a very simple model of our system. It shows mutual relationships between subsystems. And an essential feature of control systems is feedback, which we saw in the last example. We will see feedback over and over and over again. Feedback makes control robust, possible. I mean, that's why I give you feedback through midterm tests and through quizzes, so that we have a stable system here, learning system. Questions? All right, thank you very much. I'll see you tomorrow. Thanks.
刚才不说这本书，然后这个是哈巴塔，罗巴塔。
Okay. See ya. Have fun.